In question 1, part A, we want to find the horizontal and vertical asymptotes of this function, provided that they exist. If we start with the horizontal asymptote, we'll use the limit as x approaches infinity of the function. And it doesn't matter in this case if you look at positive or negative infinity, so it should be the same for both. So this is the limit as x approaches either positive or negative infinity of our function 2x squared plus 5x minus 2 all over x squared plus 7. And looking at this, I see the degree of the top and the bottom are the same, so I'm anticipating that the answer is going to be 2 over 1 or just 2. But to carefully verify this, I'm going to divide everything by x squared, the highest powered x term in the denominator. So this becomes the limit as x approaches either positive or negative infinity of, so we have 2x squared divided by x squared. We have 5x divided by x squared minus 2 divided by x squared. And this whole thing is divided by x squared divided by x squared, and then 7 divided by x squared. The next thing to do is to simplify this. So in the numerator, 2x squared over x squared is just 2. Then we have 5 over x minus 2 over x squared. In the denominator, we have 1 plus 7 over x squared. Now, I know these two terms, as x goes to either positive or minus infinity, remain the same, and all of these go to 0. So at this point, I can essentially evaluate the limit and say it's going to approach 2 plus 0 minus 0 over 1 plus 0, which is equal to 2. Again, the reason for this was these three terms each go to 0, as x goes to either positive or minus infinity. And this means that y equals 2 is, in fact, the horizontal asymptote. Now, does this function have any vertical asymptotes? To figure this out, you have to look at the denominator, and if the denominator is ever 0 for a real number, potentially you could have a vertical asymptote. And our denominator is x squared plus 7. And x squared plus 7 is not equal to 0 for any real x value. And this means there are no vertical asymptotes. So that's the answer for this part. To determine if this limit exists, we could start by just attempting to put 5 into the function and see what happens. So this is kind of like a check. So the limit as x approaches 5 of x cubed plus x minus 1 over x minus 5, is that going to work out if I just put in 5 cubed plus 5 minus 1 all over 5 minus 5? And the answer is no. The top is going to be 129, and the bottom is 0. And in a rational function, if you have a non-zero number divided by 0, this means there's a vertical asymptote in the function. So why doesn't the limit exist? If you look at the limit as x approaches, let's say 5 from the left, of x cubed plus x minus 1 over x minus 5, the answer is going to be negative infinity. And the reason for this is, well, the top is going to a positive number. If you approach 5 from the left, you'll put in something like 4, so this denominator is going to be negative. And the ratio is going to be something that's infinite, but positive over negative is negative. Likewise, if you look at the limit as x approaches 5 from the right of this function, x cubed plus x minus 1 all over x minus 5, this is going to be positive infinity. And the reason for this is from the right, the top is still going to go to a positive number, the bottom is still going to remain positive. It's going to become infinite, but a positive over positive is something going to positive infinity. So the limit does not exist. And the reason is we have a vertical asymptote because on the left, one side is going to negative infinity, and on the other side, from the right, it goes to positive infinity. In question 2a, we have this function g of x that depends on a. can we find a value for a so the function is continuous at x is equal to 2? For the function to be continuous at x is equal to 2, we need the following. The limit as x approaches 2 of the function has to equal the value of the function at 2. And specifically, the function has to exist and this limit has to exist. For the limit to exist, we need the limit as x approaches 2 from the left of the function to equal the limit as x approaches 2 from the right of the function. So what we will do is figure out both of these limits by using this function and set up an equation to solve for a. Let's start with this one here. The limit as x approaches 2 from the left of the function g of x is the limit as x approaches 2 from the left of, well, if we're coming from the left, we're using this part of the definition because from the left means less than 2. So we're taking the limit of x squared plus 3. And we can simply substitute 2 in place of the x to get 2 squared is 4 plus 3 is 7. Now the limit from the right, the limit as x approaches 2 from the right of this function, means we will use this part of the definition. So therefore, this is the limit as x approaches 2 from the right, and we have x plus a. Now here, we'll put 2 in place of x, and a is the thing we're trying to solve for. For this limit to exist, these two limits must be equal, which means we can equate these two things here. From this work, we can say, okay, well, 7 must be equal to 2 plus a. And by solving for a, we get 5. So by choosing a equal to 5, the limit from the left is going to be equal to 7. Actually, so is the limit from the right, so this limit exists. Furthermore, the value of g at 2 is equal to 2 plus 5, which is 7. So this statement is true. The limit as x approaches 2 of the function is equal to g of 2. In question 2, part b, I want to determine if this function f of x is differentiable at 3. So the question we're asking is, does f prime of 3 exist? And as a reminder, f prime of 3 is equal to the limit as h goes to 0 of, okay, so that's going to be f of 3 plus h minus f of 3 all over h. If we're trying to determine if a limit exists, we should consider the limit from the left and the limit from the right of this function. If they're equal, it means the limit exists and therefore the derivative exists. If they're different, it means the derivative does not exist. So let's look at the limit as h approaches 0 from the right of f of 3 plus h minus f of 3 all over h. This is the limit as h goes to 0 from the right of, since we're coming in from the right, we're talking about this part of the definition. So f of 3 plus h means put a 3 plus h in place of x. So we have 4 times 3 plus h minus 1. And then we want to subtract off the value of the function at 3. F of 3 is equal to, well, here you would put 3 in place of this x, which gives you 12 minus 1, which is 11. Continuing by simplifying this limit, this is the limit as h goes to 0 from the right of, okay, when we simplify the function, we get, let's see, 12 plus 4h minus 1 minus 11 all over h. And this is the limit as h goes to 0 of, well, we have 12 minus 1 minus 11, which is 0. So we're left with just 4 and h. And in the denominator, we already have an h. In fact, there's not much left over, so I'll just erase this line here. Since we can cancel the h's, this h cancels with that h, this is the limit of just the number 4, and therefore the limit is 4. So when we come in from the right, the limit for the part of the derivative goes to 4. But what if we approach from the left of the same function? we have that this is the limit as h approaches 0 from the left. And since we're coming in from the left, we're now using this part of the definition. So I'm going to put a 3 plus h in place of this x. So we get 5 times 3 plus h minus 4. Then we have to subtract off what f of 3 is equal to. And that's no different than the f of 3 here. To get f of 3, you have to look at this part of the definition and put 3 in place of x. It still gives you 11, so I'll put that number here. And this is all divided by h. So this is the limit as h approaches 0 from the left of, if we simplify the top, that's 15 plus 5h minus 15, all over h. So this is the limit as h approaches 0 from the left of, well, we have 5h over h. And we can cancel those h's, so this cancels with that. That means our limit is just 5. So does the derivative exist? And the answer is no. The left-hand limit is equal to 5. The right-hand limit is equal to 4, and they're not equal. If they're not equal, this derivative does not exist. Okay, let's evaluate this limit or explain why it does not exist. If you try to put 1 into all the x's, the top is 0 and the bottom is 0. So we have a 0 over 0, and this means potentially the limit does exist. To compute what it's equal to, we should try to factor the expression. So this is the limit as x approaches 1 of, in the top, you want to factor 2x squared minus x minus 1. And in the bottom, we want to factor x squared plus 4x minus 5. For the denominator, you have to have an x and an x. That'll be a positive 5 and a minus 1. In the numerator, you'd have to have a 2x and an x. I think we're going to have a minus 1 and a plus 1. Thinking ahead, the fact that this 1 here created a 0 in both the numerator and denominator meant, well, there'd have to be an x minus 1 that probably factors out of the expression. But since it did factor, we can cancel them. And this means this is equal to the limit as x approaches 1 of 2x plus 1 over x plus 5. And we now can just simply put the number 1 into all of the x's. And this gives us our answer of 3 over 6, which is equal to a half. All right, what is the limit as theta approaches negative 7 of sine of theta times pi over 14? Can we simply just put the number negative 7 in place of theta? And this time we can. So this is sine of, we'll have negative 7 times pi all over 14. And we can simplify this. This is sine of, that's going to be negative pi over 2. So what does sine equal at negative pi over 2? I like to think of a unit circle for help. So this is 0, this is pi over 2, this is pi, but the negative means you go backwards, so this is negative pi over 2. Sine is the y value on the unit circle at this point, and that y value is negative 1. And therefore, this is equal to negative 1 as well, and that's the answer for this limit. What is the limit as t approaches infinity of this fraction, which is a rational function? I see that the degree of the numerator is greater than that of the denominator, so I already know, okay, this limit is not going to exist, but we have to justify our answer. And the way we'll do this is by dividing by the highest power degree t term in the denominator, which is t to the first. So this limit is equal to the limit as t approaches infinity of, so this is 2t squared divided by t, plus t divided by t minus 1 over t. In the denominator, you have t over t plus 6 over t. And we can simplify this a little bit. This is the limit as t approaches infinity of, okay, so we get 2t plus 1 minus 1 over t. And in the denominator, you have 1 plus 6 over t. Now, the observation to make is that in the denominator, I know this is going to approach 1, and that's not a problem. In the numerator, this goes to 0, this stays 1, but 2t approaches infinity. I'm going to state that the entire answer is positive infinity. And the reason why is that if you look at the numerator, the limit as t approaches infinity of 2t plus 1 minus 1 over t, that's the same thing as the limit as t approaches infinity of 2t plus 1, again, because this thing is going to go to 0 as t goes to infinity, and this thing is certainly going to positive infinity. And if you look at the denominator is the limit as t approaches infinity of 1 plus 6 over t, and that approaches just the number 1. So you have a fraction with the numerator becoming infinite and the denominator just approaching some positive number in this case. That means your entire answer is going to be infinite. So that was because this is in the numerator. The numerator is going to infinity, and the denominator is constant, or is approaching 1. I'll say going to 1. In question 4, part A, we want to know the average velocity of a ball where the height is governed by this equation here. So h of t is the height, and we'll say it's in feet after it's thrown upward t seconds. So if we want the average velocity, that means we want the slope between 1 and 2. That is h of 2 minus h of 1 all over 2 minus 1. And the reason is the numerator is going to give you feet, the denominator is going to give you seconds, and the number you get is going to be in feet per seconds. So we just have to compute what this number is equal to. H of 2 is going to be, okay, so we get 2 times 2, which is 4, minus 2 squared, which is 0, minus, if you put 1 in place of t, you get 2 minus 1, which is just 1. And this is all divided by your denominator 1. And again, this is going to be in feet per second. The answer is negative 1 feet per second is the velocity, the average velocity on this interval. Now let's suppose that h is some positive number. What's the average velocity over this interval? So that is from 1 to 1 plus h. We can use the same idea as what we did in part A, but the difference is we'll put a 1 here and a 1 plus h here. So this time the average velocity is going to be h of 1 plus h minus h of 1 all over 1 plus h minus 1. Now, h of 1 plus h is 2 times 1 plus h minus 1 plus h squared. And h of 1, the value is equal to 1, so we subtract 1. And this is all divided by 1 plus h minus 1 is h. If we further simplify, I can distribute the 2, so we get 2 plus 2h. 1 plus h squared is 1 plus 2h plus h squared. If I distribute a negative into it, it's negative 1 minus 2h minus h squared. Then we have minus 1 at the very end. Okay, next, we can simplify. Well, we have a 2, and these two negative ones will cancel. We have a 2h and a negative 2h, and we're actually just left with negative h squared all over h. And this simplifies to negative h, and that's going to be in feet per second. And the final part for this problem is, well, what is the instantaneous velocity at t is equal to 1? So for this problem, that is h prime of 1, which is the limit as h goes to 0 of h of 1 plus h minus h of 1 all over h. But we actually just computed this limit in part B, and we figured out that the whole thing is equal to h. And the limit as h approaches 0 of h is actually just 0. You can put 0 in place of this h. So this is how fast the object is traveling in feet per second at this very moment. The interpretation is that, okay, the ball was thrown upward, and after 1 second is where it stopped before it started coming back down again. The reason the average velocity from 1 to 2 seconds is negative is because from 1 second to 2 seconds, the ball was moving downward. In question 5, we want to use the epsilon-delta definition of continuity to prove this statement. I know it's true because if you put 2 in place of x, you get 8 plus 7, which is in fact 15. But if we're using the epsilon-delta definition, it's a two-step process. And first, we want to find a delta greater than 0 based on some given epsilon. I'm going to let f of x equal the function 4x plus 7. And we're going to assume that f of x minus 15 is less than some epsilon greater than 0. We are going to plug this function in place of f of x and simplify this expression in order to somehow figure out what delta is. So that is f of x is equal to, well, it's 4x plus 7, and we subtract 15. And if we take 15 from 7, we get that 4x minus 8 is left over. And the observation here is, well, you can factor a 4 out from both of those terms. So you can say, well, that's really 4 times x minus 2. We can break this apart as 4 times the absolute value of x minus 2. And this is a thing that should be less than epsilon. Since our limit is approaching 2, I wanted to see an x minus 2 in absolute value, and I have it. And if you want to solve for this thing, you could divide by 4 over to this side. So that is, I know we want x minus 2 to be less than epsilon over 4, and that's going to be our choice of delta. Now the second step is to actually prove this. So we're going to look at a proof. And the proof goes like this. You let epsilon greater than 0 be given. And then you choose delta equal to epsilon over 4, and this is certainly a positive number. If epsilon's positive, then delta's positive. Next, we assume that 0 is less than x minus 2 is less than delta. Using this as our assumption, can we prove that f of x minus 15 is less than epsilon? I think it's going to work out, but to write it, you'd say, then f of x minus 15, okay, well, that's equal to 4x plus 7 minus 15, which is equal to the absolute value of 4x minus 8, which is equal to 4 times x minus 2 in absolute value, which is the same thing as 4 times the absolute value of x minus 2. We just assumed that this thing was less than delta, so I can say this whole thing here is less than 4 times delta. But delta was equal to epsilon over 4, and 4 times epsilon over 4 is epsilon, and this concludes our proof. In question 6, we're going to use the intermediate value theorem to justify that this polynomial has a real root on this interval. And what that means is there's got to be some number that when you put it into the function, you get 0 back as your answer, and that this number must lie between 1 and 4. The intermediate value theorem says that if you know the value of the function at one endpoint, and you know the value at the other, and your function is continuous, you get every single y value between the left and the right endpoint. So for starters, is p of x continuous? And the answer is yes, it's a polynomial. And they are continuous on their entire domains. So it's certainly continuous on this interval too. The next thing is, what's the value of the function at 1? So here we can take the number 1 and put it into this function. And when we do that, we get 1 minus 2 plus 2. And this simplifies to, okay, so that's going to be negative 1. Second step is, what about the other endpoint, 4? If we put this into the function, okay, so we have 4 cubed, which is 64, minus 2 times 4 squared, which is 16, minus 2 times 4, plus 2. So p of 4 is equal to, okay, so that's 64 minus 32 minus 8 plus 2. And when we simplify this down, we get that p of 4 is equal to 26. So if you're thinking about your function and what your function looks like, we figured out at 1, it's equal to -1. And over here at 4, it's equal to positive 26, which is up here. And I'm not 100% certain what the function looks like, but the fact that it's continuous means it's never going to have a break in the graph, and it's got to go from one point to the other. And because of this, there is a spot where the function is equal to 0. This is a real root. So yes, there exists a real root. So to carefully state this, as the number 0 is between the two y values, p of 1 and p of 4, by the intermediate value theorem, there is a real root in the interval from 1 to 4. In question 7, let's use the limit definition of the derivative to find f prime of x for this function. So the way this will work is, I want to find f prime of x, and this is the limit as h goes to 0 of f of x plus h minus f of x all over h. That's equal to the limit as h goes to 0 of, okay, so the function is 2 over x, so we have 2 over x plus h. Then we have minus 2 over x, the function itself, all divided by h. When dealing with fractions within fractions, a good move is to multiply by the least common denominator, which is x plus h times x. And the reason is when you distribute it to the numerator, it's going to cancel the fractions within fractions. So that means we get the limit as h goes to 0 of, when this gets multiplied here, the x plus h's cancel, leaving us with the x, so we have 2x, minus, when this gets multiplied here, the x's cancel, and I'm left with the x plus h, so we get minus 2 times x plus h. And in the denominator, I'll just leave it as h times x plus h times x. I don't want to start multiplying in the h because eventually I'd like to cancel this thing. Here I'll distribute the -2, and so this is the limit as h goes to 0 of, so we get 2x minus 2x minus 2h. In the denominator we have h times x plus h times x. I'll continue my work up here. This is the limit as h goes to 0 of, and in the numerator we just have 2h. In the denominator we have h, x plus h, and x. I can now cancel the h, and this is great. And the reason is, the limit as h goes to 0 of the function 2 over just x plus h and x is written in a way where you can now just put 0 in place of this h. And in fact, when you do, this is x, and this is x, which is x squared. So this is -2 over x squared. This is the formula, f prime of x, the derivative of 2 over x.